Good morning, students. Today we're going to look into Cyclone, a gas cleaning technology. Cyclones are used in solid gas separation. So, in fluidized bed, if there are particles that entrains, for example, in this case, so this is an example of a fluidized bed, and you can watch this in this YouTube link. So these are the entrained particles. Particles that escapes these fluidized beds. So these particles can actually be recovered through a gas cyclone. So this is the cyclone. This cyclone separates the particles and returns it to the fluidized bed. So it is also an important process in pneumatic conveying. So in pneumatic conveying, air or gas is used to transport solids from one point to another. So once it has reached the point, then we have to separate the gas at the end of the transport line and collect the solid particles. So for example, like this one, so this is the end of the pneumatic transport. So at the end of the pneumatic transport, it reaches a cyclone, and this cyclone will collect the particles that is required through a cyclone and then down to a hopper, and then the gas will be the gas or air will be released or reused for pneumatic transport. Solid gas separation is also used in combustion. Okay, so for example, this one where combustion takes place. So this combustion, this burning process will carry hot air and some fine particles, fine dust. So what do? It goes through cyclones. It goes through cyclone to separate the escaping dust and release the hot air. So that's where we use this gas cyclone for solid and gas separation. Cyclones are used for relatively large particles, and these cyclones, this is an example of a cyclone, usually consists of a cylindrical part here, a shell, and then it has got a conical base and a dust hopper at the bottom, and it has got an inlet for the dirty gas plus particles to enter, and then it has got an outlet where the clean gas exits, and then this is where below the hopper is the exit for the particles that has been collected. So these cyclones cannot be used on its own. I mean, it cannot be the only cleaning agent. It's actually insufficient to meet the stringent emission standard. So it acts as a pre-cleaner. So it is a pre-cleaner to remove bigger particle size, and after that, further cleaning needs to be done using other separation mechanism. So this is a graph for, it's a typical efficiency curves for different gas solid separators. So as you can see, cyclones are efficient for bigger particle size, more like it's bigger than 1 or bigger than 10. Bigger than 10 cyclones are better. Okay, so for smaller particle sizes, we can use wet separator, electrostatic precipitator, or much smaller is the filter. Filters we covered in the packed bed chapter in this course. So these two, if you're curious to know how it works, you can actually look at the YouTube link given below. So that will give you what are these separators. So usually, if let's say the particles are bigger than 100 micrometer, we just use gravity settling for the bigger particles to settle down. And if it is less than 10 micrometer, then we require energy intensive method such as these three. Okay, so gas cyclones we can use for a bigger particle around this range, even 10 to 100. We can still use for one, but then we just have to make it, we have to design the cyclones for higher efficiency. To achieve 50, yeah, we need about 10 micrometer. So gas cyclones are not suitable for suspension with large proportion of particles less than 10 micrometers. So there's too much of this size of particles, so gas cyclones will not do so well. So if you notice, the efficiency hardly even reaches 50%. It's not even 50% for the ones below 10 micrometer. Okay. So let's look into the cyclone mechanism. So cyclone operates on a principle that the aerosol material, or the particles, the fine particles or the dust materials in the carrying gas stream has greater inertia than the gas. So the particles has greater inertia. So this is how the particles will enter. This is the dirty gas inlet. So it is expected to spiral downwards in this motion. Okay, so if you can see, it's actually as in the right-handed down, and then as the particles spiral down, it is expected to hit the walls of the cyclone and then slide down to the bottom to be collected. And the gas, once it hits the bottom of the cyclone, will spiral upwards in a reverse direction and leave the cyclone. Okay, so this is the pathway of the particles. It hits the wall and it follows the wall direction, whereas this is the pathway of the gas, where it is directed like a cylinder. Here I have shared two YouTube links for you to watch, so you can watch how two different types, slightly different types of cyclones works, where the particles spirals downwards and the gas is the clean gas exits at the top of the cyclone. Let's look into cyclone characteristics. For any cyclone, the radius of motion, that means the radius that is moving, the particle mass and the particle velocity are the three factors which determine the centrifugal force on each particle. So the fact that it spirals down, the vortex, is actually centrifugal force. So for cyclone, the removal efficiency is preferred to be between 75 to 99%. We'll discuss why it could not achieve 100% later. And then particle size range is between 1 to 100 micrometer. So, but as mentioned previously, it's best to be from 10 to 100, because if too much of less than 10 micrometer particle size range, the cyclone could be inefficient as well. And this is a very simple setup. Cyclone is a very simple setup. It is low cost and low maintenance as well. So this cyclone has two basic forms. One is a tangential inlet and the other is the axial inlet. So it's clearly it's shown in this diagram. So this is the tangential inlet, where it goes in tangentially, where the dirty gas goes in tangentially into the cyclone, and this is the axial inlet, where the gas goes in actually in axial form here, still at the top, and then it still follows the same principle, same cyclone principle, and the gas is let out. In this case, the gas goes in at the bottom. Okay, this at the bottom, and the clean gas exits at the top. So this is the example that you saw in the YouTube, where there's an additional inlet of air that actually brings the particles down. Okay, so this is a clearer picture of the cyclone inlets. So if this is the inlet, so it goes in tangentially, it goes this way. Okay, and for axial, so it all goes in into, like, this is like a fan, like our exhaust fan. So it attracts the air, dust laden gas here, and then it again spirals down and let the particles settles down, and the clean gas is let out to the top. Let's look into types of cyclone. The conventional type cyclone is known as standard cyclone. This standard cyclone can be modified into high efficiency cyclone and high rate cyclone. High efficiency cyclone gives high recoveries but has relatively small inlet and gas outlet orifices. The high rate cyclones have lower efficiencies but much higher gas capacity. So usually we use high rate when we have a high rate of particle laden gas that needs to be treated. So that's when we use high rate cyclone. So this is a standard cyclone, and it has got a particular characteristics. For example, the length of the cylinder, this length of the cylinder should be twice the size of the diameter, which is D. So likewise, the length of the cone, diameter of the exit, height of entrance, width of entrance, diameter of dust exit, and length of exit duct. It is all related to the diameter, this main diameter. Okay, so for high efficiency, it is slightly different. For example, if we look into this part, okay, this part is half D. So this part is H. So H is height of entrance, is half of D. Oh no, this H is height of entrance. We want to know this one, which is L3. L3 is the length of exit duct. So length of exit duct for the standard cyclone is 1/8 of the diameter. But for high efficiency cyclone, it is 0.5 of the diameter. And then for medium efficiency, which is also the high rate cyclone, the length of exit duct is 0.875 diameter. So that's how these three different types of cyclones differs from one another. So this is also another diagram showing the high efficiency cyclone and medium efficiency or high gas rate cyclone, where you can see the height is about the same, but the orifice for the high efficiency is comparatively smaller than the high gas rate cyclone. So these ratios are quite standard, but it differs slightly from different types of cyclones. So the ones that we use in this textbook is Stamen cyclones. So this is Stamen high efficiency cyclone, and this is Stamen high capacity, which is high gas rate cyclone. So if you notice, there's also Swift cyclone, which has got its own parameters, and Lappel cyclone. Okay, so in our course we'll be using Stamen cyclone. Okay, so here you can see when there is a change in the design, that means on the length of a cylinder, on the parameters of a cyclone, it affects the pressure drop and the efficiency, subsequently the cost of the operation as well. Let's look into the flow characteristics of cyclone. The flow characteristics of the cyclone is given by Euler number here. It's a resistance coefficient which relates the total pressure drop that happens in the cyclone to the gas velocity. Okay, so this total pressure drop between the inlet and gas outlet includes the frictional pressure losses in the inlet and the outlet, as well as the changes in the direction. And this gas velocity is governed by this equation. So this is the flow rate equation, where Q is the gas flow rate and D is the inside cyclone diameter. Okay, because the cyclone will have an inside diameter and an outside diameter. So this one is the inside diameter. So this Euler number is actually a ratio between pressure forces and initial forces. This is initial force. So it's constant for a given cyclone geometry and it's independent of the body diameter. But it's dependent on the internal diameter of the cyclone. Okay, let's look into the cyclone efficiency. So the total material that is found in a cyclone is the total of fine product and coarse product. Okay, this is the total solid mass that is found in the solid exits. So the efficiency of a cyclone is defined by the solid product that is separated from the gas flow. Okay, and this equation gives you the component balance for each particle size in the solid product. So the total efficiency of the cyclone is based on the mass of the coarse product that is separated from the cyclone, and so it is a ratio from the total solid mass in the separator. Okay, and grade efficiency is the mass of solids of a particular size in coarse product over the mass of the solids of size X in the feed. So this is the ratio. So that is grade efficiency. So we can find out for each solid size how efficiently has it been removed in that particular cyclone. Let's look into critical particle diameter. So this is the diameter we are expecting to look at to define a particular cyclone, meaning to say what particle size will be efficiently separated, that means 100% separated in a cyclone. So for that we have to do a force balance for a particle size. So let's say it's in equilibrium, and it is governed by these forces. Okay, so when we make an equilibrium of these forces, we get this equation. So this is the critical particle diameter. So in theory, this critical particle diameter at this point should give us 100% separation. That means any particle size from critical diameter and above, there should be 100% recovery. But that is not the case in real situation. In real situation, there's always particles which are slightly smaller than the critical size, as well as particles that are bigger than the critical size. So in real separation process, the curve is a S-curve. So because of this phenomenon, we use a grade efficiency of 50%. We use a grade efficiency of 50%, which is X50, to define an efficiency of a cyclone. So to define an efficiency of a cyclone, we look into X50. So this X50 is also known as equiprobable size or a cut size of a cyclone. So X50 means in a large population of particles, 50% of the particles of this size will appear in the coarse product. So that's how we define a cyclone efficiency. Okay, to scale up a cyclone, we use Stokes number. So this is Stokes number. Stokes number is a ratio of centrifugal force to drag force. So like Euler number, Stokes 50 is independent of Reynolds number. So for concentration less than 5 gram per meter cube, Euler and Stokes 50 is constant. So why is this 50? It's because of the X50, which defines the cyclone efficiency. So for example, in this book we use high efficiency Stamen cyclone and high rate Stamen cyclone. So these are the fixed value of Stokes 50 number and Euler number. Okay, so once when we use the Stokes number, if we use the Stokes number, we can actually plot a curve for different efficiencies, and so we can calculate the grade efficiency. That means the efficiency to separate different particle sizes in proportion to X50. So this is the graphical representation of the grade efficiency. So this is the relative size or the diameter over D50 and the efficiency. So the collection efficiency of a particle of both larger and smaller than D50 can be determined by the ratio as given in the graph here. So we can also get the overall efficiency by plotting the collection efficiency against the particle size. So here we directly look for the efficiency for the particle size. So for like 5 micrometer, it's about 27%. Let's look into the range of optimal operation for cyclone. So theoretically, this is the total efficiency over gas flow rate. So theoretically, the efficiency of a cyclone should increase with increasing gas flow rate. However, in practice, this is not the case. The total efficiency will actually drop due to re-entrainment. So what does re-entrainment means? So when it's operating between A to B, that is the max optimum operation, wherein the dust is separated to the bottom and the gas flows to the top. But beyond this point, re-entrainment means the gas, the solids gets carried away with the gas that is leaving the cyclone, because the flow rate is too high, so there's high turbulence, so the particles gets enough energy to leave with the gas that is leaving the cyclone. So that's why we should be operating between A and B, and this A and B is usually between 50 to 150 millimeter water gauge or 500 to 1500 Pascal. Okay, so anything below A, the low limit, is like a settling chamber. So it's like if you let a gas in and you let it to settle down on its own. So it is very, very low efficiency due to the low velocity of the particles. But if it is beyond B, then it's a waste of energy, because the efficiency declines as well, because the particles gets carried away with the clean gas. There are some design consideration to look into for cyclone. So generally, high dust loadings will give us high total separation efficiency. So like dust loading above 5 gram per meter cube can actually give us high efficiency. And then for the different types of cyclones, so if we are looking at high efficiency cyclones, we are expecting high recoveries. We want high recoveries. Therefore, the inlets and the outlets orifice should be designed smaller. And if we don't mind the efficiency, but we have a large amount of gas inlet, so it should be designed with large inlet and gas outlet, and it's usually shorter. So a well-designed cyclone has got a correlation between the Euler number and the Stokes 50. So high values of resistance coefficient, so high value of Euler number will lead to low value of Stokes 50, which means low cut sizes will give you high efficiency and vice versa. And then we should also look into the abrasion points. There are two main critical points. One is just beyond the inlet opening. Once when the gas comes in at the highest velocity, so at that part there could be abrasion, and in conical parts near the dust discharge, because that's where the particles will hit the wall of the cyclone. So abrasion can happen to the equipment. And then it can also cause attrition of solids. That means the solids can break down because it's hitting the wall at a higher velocity at these points. Okay. Other design considerations are blockages. Blockages can happen due to mechanical defects like bumps on the cyclones or protruding valves and gaskets. So if there's some uneven surface or rough surface, or even there are physical or chemical changes in the solids like condensation and vapor, so it can actually build up on the surface and cause blockages. So that will affect the efficiency of a cyclone. The other factor that we need to consider is the discharge hoppers and diplex. So these discharge hoppers should be designed properly so that the particles that are separated can easily be released. So these diplex are like a pipe that allows the release of the particles for the next unit operation or for storage purposes. So if this gets stuck, so this will also affect the cyclone. And cyclones can also be operated in series and parallel for different reasons. So if let's say we have a wide range of particles sizes that needs to be separated, so that can be done in series. So large particles can be collected in the first cyclone, and a more efficient cyclone to collect the small particles can be designed at a later part. So literally the gas will flow into the first one, and this cyclone will be designed for a larger particle size, and then the gas that leaves the air that leaves this cyclone will feed into the next cyclone, and so on. Okay, so with that we can design the cyclones to cater to the range of particle size that we are looking at. And here we collect the different particle size of the dust. So this can increase the overall efficiency and overall pressure drop increase. And this series also reduce dust loading into the second cyclone. That means you don't have a very high load of dust that goes into it. The bigger particles has been removed here, so there's a smaller range, lower dust loading that goes into the second cyclone. So this avoids problems like plugging and abrasion. So we can also have parallel arrangement. So if we have a large volume of gas that need to be separated, so we can use a parallel multicyclone, so wherein the dust laden air comes in through one inlet and it goes into separate cyclones. So it gets separated, so there's one general dust collector, and the fine and the clean or the fine dust is removed at the top. So there's only one duct in and one duct out, and one collecting hopper. So which type of arrangement that is required is dependent on the process. So in the following slides, I have presented different types of parts that are used in the cyclone. So please have a read. For a cyclone inlet, so we saw in the beginning just now a simple design, which is a tangential entry such as this. But this design can also be modified for high efficiency cyclone. And then we also have helical cyclone, where this top part is slightly different. It's still tangential, but then it's not a flat flat cylinder, but it's slightly curved down. So that's helical entry. And then we have involute entry. So it goes semicircle and then directs it. So it's in the tangential, it goes in and directly gets into the cylinder, but this one is involute entry, so it's directed to a certain point before it circulates down. Okay, and then there are also different types of discharge system, the diplex that we were talking about. So it can just be a simple manual gate, where if you slide this gate out, then it just drops to the collector. It can be a rotary valve, so this can be a continuous discharge system. Okay, it can be a discharge screw feeder, so it screws through, okay, to free the particles from the cyclone. It can also be an automatic flap, so once it becomes heavy, so it will drop, it will open, so these particles that builds up will drop to the bottom. So this is a flap motion. And then I've also attached some monitoring and maintenance plans for cyclone. So we have daily monitoring and maintenance plan, weekly monitoring and maintenance plan, where here we have to look into the discharge valves and operations. For the daily, we are more interested in the efficiency of the cyclones. So here we look into the parts of it. And then there are quarterly monitoring and maintenance plan, where we look into the ductworks and hoods for any leaks or any component failures. And we also have annual inspection to look into the whole barrel and the tubes to see if there are any dents or deposits that can actually affect the efficiency of the cyclone. Okay, so that's all for this lecture. So let's look into the example questions in the next video. Right, let's look into the worked example of a cyclone design. So these examples are from Martin Rhodes' textbook, Introduction to Particles Technology. Right, so in this question, they want us to determine the diameter and number of gas cyclones required to treat this amount of ambient air with these characteristics, viscosity and density, and the solid density is given at a suitable pressure drop. So for this question, the pressure drop is given in terms of 100 meter height, and then the desired cut size is 4 micrometer. And this cyclone design uses Stairman high efficiency with the Euler and Stokes 50 number, fixed number. This is a constant, yeah. So first of all, we can determine the pressure drop from a given 100 meter gas height of a cyclone. So it's the pressure drop at this height, so we times by the density and gravity, so we get the total pressure drop. The first thing that we can calculate is the characteristic velocity. So we can use the Euler equation from equation 9.1. so your Euler is equals to total pressure drop over density V square over 2. So since we have the total pressure drop, we know the density of the fluid, so we can find the V. Then the next, we can use that V. We used equation 9.2, which is V is related to the flow rate of the gas square. Okay, so we know the flow rate, which is 2 meter cube per second. So we know the V now, so we can calculate the D. So now we get the diameter. Next we use equation 9.21, which is the STK 50 equation. Okay, this STK 50 is equals to x square 50 times by density of the particles and the velocity over 18 mu viscosity of the gas and the diameter that we just calculated, this one. Okay, so if we use all these values that are already known, this is particle density, yeah, so we can find our cut size for this cyclone. Okay, so from this cut size we can see this more than the cut size given in the question. Sorry, so this is the cut size desired in the question is 4 micrometer. So this is too high, and we must therefore opt for passing the gas through several numbers of cyclones. So there's more than one cyclones in parallel. So that's why the cut size was smaller. So this is big. So assuming there are n number of cyclones in parallel, so we take the flow rate would be total flow rate, which is the 2 meter cube per second, divided by n numbers of the cyclone. So again we use equation 9.1 and 9.2 to calculate the new diameter. Okay, now the diameter will be will have the n unknown. Okay, so this is the new diameter, and we substitute in equation 9.21 to obtain the required cut size for D, and the required cut size, which is 4. The required cut size is 4, and the V is still the same as calculated originally because this is determined solely by the pressure drop. So then we can find that the N is 1.386. So we can't have 1.386 number of cyclones, so we need at least 2 cyclones. So now with N is equals to 2, then we reverse calculate. We can calculate the cyclone diameter from this equation, and we can get the actual achieved cut size for this diameter. So if the N is 2, the diameter becomes 0.717, and the V remains the same because it is not affected by the diameter, and the cut size where we use Stokes 50 equation 9.21 from the textbook, we get 3.65 micrometer. So to answer the question, we need 2 diameter stem high efficiency cyclones in parallel arrangement with diameter size 0.717 meter, and that will give us a cut size of 3.65 micrometer with a pressure drop of 1177 Pascal. Okay, so that is solution for question 1. And then we have worked example 2. So this one is a range of feed analysis. So the sizes has been given. So the feed analysis, that means the mass that has been obtained for each grade, as well as this is the total mass for each grade, and the cost product size. So from these results, determine the total efficiency of the cyclone, and then we plot the grade efficiency curve to show the X50 cut size is 10 micrometer, and then we have to determine the diameter and number of cyclones to be operated in parallel. Okay, this one is similar to equation worked example 9.1. and what is the actual cut size of your design after the changes? Okay, let's look into it. Okay, first of all, from the results, the total mass was 100 and the cost product was 65. Okay, so the total was simply adding up this, okay, for the mass and also for the cost product. So we get it in mass, and the total efficiency is affected by the mass of the cost products, so we get the total efficiency as 68.56%. And then we do the grade efficiency. So from equation 9.7 that we discussed, so for each grade we can also identify its efficiency using this equation or this equation. Okay, so that will give us this data of grade efficiency. So in this example, we just use directly the mass. So we just divide the mass of cost product for each grade over the total. Okay, so for example, 0.1 divided by 10, you get 0.01. 5 divided by 1, you get 1. So this is how we get this table, grade efficiency. And then we plot this table, grade efficiency to particle size. So this is the range. You can take the mean of it or the high range. So you can here I think they took the mean. Yeah, so between 5 and 10, this is the point. So they took the mean of each range and they plot this value. So once we plot, we look for 50% efficiency. What is the size? Is it 10? And yes, it's correct. It is x50 is equals to 10 micrometer. Okay, so that answers question B. And next is we are looking for determine the diameter and number of cyclones and the actual cut size. Okay, this part is calculated for interest just to use this equation. So we can also use this equation. So how do we get this information? So what we do from the question, so this is the question, this is the mass of the product. So if we take 0.1 divide by the total that we calculated just now, the total was 68.56, you will get 0.00146. So that's how we get for cost product as well as the feed analysis. So 10, so if this is 10, divide by the total, which is 100, so you get 0.1. So this is how we get the frequency of each size range. And then we use the efficiency. So we calculated the efficiency here, so 6856. So you times by for example, if I want to calculate for 10 to 15%, I want to know what is the efficiency like. So 0.6856 times the cost efficiency over the total efficiency. So this is the grade efficiency for this size range. Okay, so this is how we use this equation. Right. Okay, then for question part C, so we have to determine the diameter and number of cyclone. So again, we start off with the Euler equation. Okay, we have the Euler number, the fluid density, and the pressure drop. So we get the characteristics velocity. Okay, then we substitute it to the flow rate equation. Okay, here we substitute the Q is equals to flow rate, the total flow rate, divide by the number of the cyclones. Okay, so then we can identify our D in terms of N. And then now we substitute expression of D and the required cut size x50 in equation 50. So this is the Stokes equation. So the D is substituted here. The required size was 10. STK 50 just now, this one was 10 micrometer. So that's why it's 10 micrometer, 10 to the power of 6. So this solves for N. So therefore we can see if it is 1.88, so we need 2 cyclones. So now that we know the D is so now we can solve for D because we already know the N. Okay, so the D is 1.67. So that is part C. And finally, the part D, the actual cut size achieved with 2 cyclones is calculated with the D and the V that we have obtained. So we use the X50 and to find out what is the actual cut size. So this is it, and it is very close to the desired cut size. So in summary, 2 cyclones with a high efficiency and this Euler and Stokes 50 constants. The diameter required is 1.67. It operates at 1200 Pascal and achieves a cut size or equiprobable cut size at 9.85 micrometer. So that's how we solve this question. Okay, that's all. So please do the exercise given to you in the slides. Thank you.